Navneet, your voice is breaking.
Navneet, unmute yourself and then speak again.
Okay, good morning, everyone. Now I am audible. Please confirm.
Yes, Navneet, please continue.
So we are about to start this session. We can wait 1 2 minutes more for joining of other participants also. मोबाइल देखो लालच में Okay, now we can start. Please confirm once again. Am I audible to everyone? Please confirm. हाँ, now you are audible, Navneet. You can start. Okay, sir. Okay, thank you. So, good morning to Dr. Deepak Kumar, sir, respected faculty members, and all the dear participants present here. I hope you are having a wonderful learning experience in this ongoing 2 week online faculty development program on grid resilience and adaptive control evaluation in power systems, that is GRACE PS 2025, jointly organized by the Department of Electrical Engineering, MNIT Allahabad, and the Department of Electrical Engineering, NIT Patna. I am Navneet Pathak, and it is my privilege and honor to introduce our distinguished speaker for this session, Dr. Deepak Kumar sir. We are delighted to have Dr. Kumar sir with us today and look forward to gaining from his expertise in this important title of the talk, that is unlocking the second life of EV batteries, that is a roadmap for innovation. Dr. Deepak Kumar sir has received his BTech degree in electrical engineering from UPTU Lucknow, India in 2007, and his MTech and PhD degrees in electrical engineering from Indian Institute of Technology, Banaras Hindu University, Varanasi, India in 2009 and 13 respectively. He is currently serving as an associate professor in the Department of Electrical Engineering at Motilal Nehru National Institute of Technology, MNIT Allahabad, India, where he has been a faculty member since October 2012. Prior to this, he worked as an assistant professor in the Department of Electrical and Instrumentation Engineering at Thapar University, Patiala, from June 2012 to October 2012. He also served as doctoral fellow with the Control System Research Group, School of Electrical, Electronic and Computer Engineering, the University of Western Australia, Perth, Australia, from March 2017 to February 2018. Dr. Kumar sir has over 13 years of teaching and research experience. He has supervised 30 MTech theses and 5 PhD dissertations, and he is currently guiding 4 PhD scholars. His research interest includes frequency limited model reduction, fractional order modeling and control, and application of control in power systems. He has published over 100 research papers in reputed international journals and conferences. Dr. Kumar is a senior member of IEEE, a member of IEEE Control System Society, the IEEE System Council, and a life member of System Society of India. He is a reviewer of leading international journals of IEEE elsewhere, Valley, uh, Taylor and Francis, and Springer. Dr. Kumar has actively contributed to organizing several international conferences. He served as conference chair of the IEEE Student Conference on Engineering and Systems, technical program chair for this SEES 2019 and 2024, and also for ICP CEAS 2019, publication chair for UPCon 2020, and organizing secretary for ICP CES 2014. He has also been an associate editor for the Australia and New Zealand Control Conference, that is ANZCC, in 19, 20, and 22, and also for 2025. His paper titled as Design of 2 Degree of Freedom Internal Model Control Configuration for Load Frequency Control using Model Approximation, received the Best Paper Award for the year 2021 for, from the International Journal of Modeling and Simulation, which is a journal of Taylor and Francis. So, sir, we are truly honored to have you with us today. With that, I now invite Dr. Deepak Kumar, sir, to kindly take over the session from here. Sir, the time is all yours. Thank you, sir. Thank you, everyone.
Thank you very much, Navneet. So, am I audible to all? Navneet, please confirm.
Yes, sir, you are
Yes,
quite
sir.
audible, sir. And the screen is also visible.
Right. Right. Thank you very much. Right. So, a very good morning to all present here. And it's a privilege to be here to discuss and important topic, that is unlocking the second life of EV batteries, a roadmap for innovation. So in this lecture, we will see second life utilization of EV batteries with a specific focus on Indian perspective. And we will see this topic is a combination of technological innovation and environmental sustainability and national strategy. So over the course of this lecture, we will have a comprehensive journey. We'll start by understanding the scale and uniqueness of India's electric mobility revolution. And this is not just about new cars. It is about a fundamental shift in how our country is achieving growth. We'll then explore into the very heart of EV, that is its battery. We'll explore its life, its science, and the unavoidable process of how a battery degrades or ages with time. And this is crucial because to understand the value of something old, we will have to first appreciate that how it was when it was new. And then we'll proceed to the core discussion of this lecture, the concept of second life for these batteries. We'll see that what exactly is a second life on EV battery, or how does a battery transition from powering a car to powering a home or to a factory. We'll see the application of second life batteries, the benefits it offers, and we'll also see the real and complex challenges which is being faced by the second life battery industry. And this will not be a generic global overview. We'll keep most of our discussion in the Indian context, and we'll explore some of India's unique policies and also some game-changing regulations. And we will see some of the startups in India who are building the second life battery ecosystem from the ground. And finally, we will summarize our entire discussion. So before going towards retired EV batteries, we'll first see an overview of India's electric vehicle industry. And this is a complete revolution which is happening on our roads, in our cities, and even in our villages. So in this first section, we'll do three things. First, we'll look at the numbers that define this record growth. Second, we'll have a look at the unavoidable consequence which will be coming due to this growth, and that is a future tsunami of used batteries. And third, we'll frame exactly why giving these batteries a second life is not just a waste management idea. And this is important for India's economic, environmental, and strategic future. Right. So if we look at this graph, and this is taken from one of the document of Niti Aayog, and we can see that the global sales of EVs increased from 918,000 in 2016 to 18.78 million in 24. This is a global EV sales. And because of this, there has been an exponential increment in the total EV stocks also. And the total EV stock globally timed up to approximately 61.21 million in 24. And this figure also shows that sale of EV in India was around 50,000 in 2016. And it went up to 2.08 million in 24 here. And due to this, the total EV stocks in India have reached to 5.45 million in 24. So if we compare the Indian EV stocks and sales to the global, the total EV stock in India are at around 9% of the global EV stock, and EV sales in India are around 11% of the global sales in 24. And this clearly, you can see, this clearly shows the massive growth in the Indian EV market. So in this slide, we'll see some of the numbers of sales of EVs in India. And you will see that the numbers are surprising. In 24, our domestic electrical vehicle market was around 8.5 billion US dollar in 24. Now keep this number in mind. So as per the projections, this will go over $150 billion by 2030. And this is a compound annual growth rate of over 40%. And if we see this in simple terms, the EV market is expected to grow nearly 18 times in just 6 years, from 24 to 2030. And this is one of the fastest growing major market anywhere in the world. You know, this growth is just not a projection or estimation. It is happening right now. In the last financial year, the percentage of EVs out of all new vehicles sold in our country was about 7.8%. And this figure was only 1% a few years ago, which is now 7.8%. And this shows a clear and accelerating trend. The government Indian government is also targeting even further beyond this. And it is clearly stated in various policy documents of Government of India that they have a target to achieve 30% EV sales by 2030. This is the Indian target, right? So that means the sales of EV should reach to 30% out of all private car sales in India by 2030. But here, if you see, there is a very important point in terms of India. Unlike Europe or US or Western countries, where the EV market is dominated by high-end car, very costly cars like Tesla and so on. The India's e-mobility revolution, this is being driven by the common person's transport, that is two-wheelers and three-wheelers. The Indian electric two-wheelers companies like Ola Electric, TVS, Bajaj, and these make up nearly 60% of all EVs sold in India, right? So now think about that. For every 10 EVs sold, 6 are scooters or motorcycles. So we can say that electric three-wheelers are the backbone of our urban and semi-urban connectivity. And these account for 36% of total EV market in India. The electric car is also growing and the EVs are visible on the road, you can see. And the electric car sales are at around at 5% of total EV sales in India. So now the fact is, most of our EV revolution is happening on two and three wheels. And it has extreme impact on the second life battery industry. It creates a scenario that is fundamentally very different from the Western countries, right? And this tells us the type, size, and chemistry of the batteries which are going to enter our market. Therefore, to utilize these batteries, we will have to look for the logistics to collect these batteries, and we'll have to see kinds of second life applications also for which these battery will be suitable. So we'll revisit this crucial point in our discussion. Right. So if you see, millions of electric vehicles are being sold today. And every single electric vehicle which is being sold today contains a large, sophisticated lithium-ion battery pack. And these batteries are expensive. And these batteries represent around 30 to 40% cost of an EV. And every one of these pack has a finite lifespan inside a vehicle, right? And we know that the auto companies give warranty on the EV batteries for about 8 years or maybe some certain number of kilometers. And generally it is considered that a battery will reach its end of first life when it has nearly 70 to 80% of its original capacity left. And at this point, when the battery has around 70 to 80% SOH, the vehicle's driving range reduces. It reduces significantly, and it is considered less practical for daily transportation. But the important point is that the battery still contains 70 to 80% of its original energy storage capacity. But there may be many batteries that can last longer, but it is considered in overall that a battery's first life is between 8 to 10 years, like right in a demanding automotive application. So this means there is a critical time lag. The exponential growth of EV sales, which has started from 2020 that we are observing today, is creating a massive delayed wave of used battery, which will begin to crash in early 2030s. That means in early 2030s, we'll have a lots of millions of used EV batteries in our market. So now let's put some numbers here to this huge number of used EV batteries, right? So globally, the supply of used EV batteries available for second life applications is expected over 200 gigawatt hours per year by 2030, right? And for India also, this number is also huge. By 2030, our domestic market for battery recycling and repurposing will be around 23 gigawatt hours annually. And this is not just a waste we are talking about. It's a potential billion-dollar industry which is waiting to build right here in India. And think about this for a moment. If we simply discard or immediately recycle these battery, we are throwing away a valuable resource that can serve for many useful applications. And this is the crux of the matter. We are at critical stage and we can choose to see this coming wave of EV batteries, the used EV batteries, as a hazardous waste problem, a logistical environmental nightmare, or we can choose to see it as a massive resource opportunity. It can be a national asset and it can power our future. So if we see the diagram right hand side, the EV adoption rate has increased in recent years tremendously, which I showed in the previous slide also. So therefore, the decisions, the policies, and the system which we will construct today, and these will determine which of these two futures, whether it is hazardous waste problem or it is a resource opportunity. And out of these two futures, we are going to see. So overall, we can say that for our country, second life battery can play a very important, crucial role in improving energy access. And we know that despite significant progress in electrification, nearly 240 million people in India still lack reliable access to electricity. And these second life batteries can provide cost-effective solutions for rural and remote areas of India if we combine these batteries with renewable energy sources, right? So you can see that this topic is very critical and it is not important just for us. It is important for everyone because the concept of second life batteries, it aligns perfectly with India's major objectives. First, I think the most important objective is economic importance. You know that India is building its EV revolution on imported technology, right? India is importing all the lithium ion cells. And along with this, all the majority of critical raw materials which are required for manufacture the lithium ion batteries, these are also being imported, right? So this is the major issue with the EV revolution, right? And this creates a significant economic weakness also. It can create a geopolitical risk also for us and the supply chain disruptions also. The every battery that we can give a second life or every gram of lithium or cobalt we can recover through recycling from these batteries may be small. It may be small, but it will be a crucial step in reducing this import dependency, right? And this is exactly a robust circular economy for batteries. And this is a direct path for resource security and a stronger currency in our country. So further, the second one is, and the economic opportunity is very huge, right? So the studies says that if we effectively utilize the second life batteries or by recycling, India can save approximately $2 billion annually, right? So it is economically very important. And this can be done through reduced material imports and by creating new business opportunities, right? So $2 billion industry we can create by the circular economy. The second is environmental importance of this. So if we simply discard the batteries after the first life of its use, then it is like we are inviting an environmental disaster. These batteries are like electric vehicle. These contain heavy metals, dangerous electrolytes, and these will be very harmful if these electrolytes or heavy metals reach our soil or water system. And we also know that the process of mining new lithium and cobalt, this is also very energy intensive, and it also contains severe environmental and social cost. So if we extend a battery's life, we are going to delay the energy intensive recycling, and more importantly, will displace the need for manufacturing a new battery, right? And which can be used for stationary applications, right? So by this circular economy, we'll be able to save huge amount of energy, resources, and carbon emissions also. The third is strategic imperative, strategic importance, right? So second life battery repurposing initiative, this is very aligned and this is perfect for the our national goals. It directly supports the climate commitment of India, that is to achieve net zero emissions by 2070. And this circular economy, this is the foundation of Atmanirbhar Bharat, or the self-reliant India mission, because it directly involves building a completely new domestic high-tech manufacturing and services industry. And in doing so, it will create thousands of new skilled green collar jobs in areas like battery testing, refurbishment, system integration, and advanced recycling, right? So from an environmental perspective, every battery we can keep in use, productive use, is one less newly manufactured battery. And this will reduce the overall carbon footprint in India, right? So when we talk about second life batteries, we are talking about energy security, environmental protection, and economic self-reliance. And hence, this topic is of national importance, right? So now we have established why second life batteries are important, or the end of life utilization, how we can move ahead. Now let's go to the what. What is the concept of second life in EV batteries, right? So we must first understand the lithium ion battery itself. The lithium ion battery, this is a remarkable piece of technology, not just a black box, right? So in this section, we are going to see a brief overview of battery chemistries. We'll see the battery from its manufacturing to its end of life in a vehicle. We'll look at the specific type of battery chemistries that are powering India's electric vehicles, because all batteries are not the same. So we'll then see the signs, how the battery age or degrade, and then we will use some simple comparisons to see some like the complex electrochemistry of the batteries. And finally, we'll precisely define what we mean when we say a battery has reached the end of its first life. And no, this is not the end of first life. This is really a new beginning. So if you see what I told you, that not all lithium ion batteries are same. There are many different types of batteries, and each battery is designed for different purpose and price point. So in Indian EV market, there are two main chemistry, right? LFP and NMC. So understanding the difference between these LFP and NMC is very important to understand the second life battery, right? So first we have LFP, and this stands for lithium iron phosphate. There is some spelling mistake here. Phosphate. Okay. So you can think of this as a workhorse battery. So LFP battery is like a workhorse battery. So the biggest advantage of LFP batteries are that it's cheaper to produce, and it uses abundant inexpensive materials like iron and phosphate. And it also avoids the use of expensive and imported material like cobalt, right? And LFP batteries are very safe due to its high thermal stability. And this is massive plus for operating in India's hot climate, right? And finally, the LFP batteries have a very long cycle life. That means it can be charged and discharged many more times, like maybe around 3,000 to 5,000 times before it degradation. for these benefits are with the LFP batteries, there are some negatives also. So LFP batteries have lower energy density, right? That means for the same weight, it provides less range. This is why LFP is highly being used in two-wheelers and three-wheelers, and which are the cost sensitive segments. But these two-wheelers and three-wheelers EVs are dominating India, right? But there are some growing numbers of electric buses and budget cars also which are using LFP. Okay. On the other hand, we have NMC, which stands for nickel, manganese, and cobalt. And this is a performance battery. The key advantage of NMC is that it has a much higher energy density. And that means we can have longer driving range. And this is the key point for premium cars. But the downsides, the negatives of NMC batteries are that it has higher cost. Okay, so this is the first negative. And the second negative is that it's reliance on cobalt. Okay, and the third point is the NMC batteries are slightly more sensitive toward high temperature. And due to this, NMC batteries require more complex thermal management. Okay, so in the table right hand side, you can see that majority of Indian electric car which are running on our road have LFP batteries like Tata Nexon, Curve, Mahindra B60, and BYD, right? And the NMC batteries can be found in the high-end model of the companies like Hyundai and MG Motors in India. So what does this mean for us? Because India's market is heavily dominated by two and three wheelers. That means our future stream of used battery or the retired batteries will be having these LFP batteries. And these batteries, because are having a robust, long-lasting, and safe LFP, right? So if you see, this is a huge advantage for our second life industry, battery industry, right? So why do these batteries retire? Just like any hard-working component, the batteries degrade over time. And this degradation is not a single event. It's a slow, continuous process which is driven by complex internal chemistry of the batteries, right? So we can simplify this by thinking the two main types of aging of the batteries. So the first is calendar aging. And this is the degradation that happens simply with the time. Even if you park your EV and don't use for a month, it will degrade. The battery will degrade. And this is an inherent chemical process. Because of that, it happens. So the best analogy for is that a piece of fruit on your kitchen counter. So even if you don't touch it, it will slowly damage. It will change its structure, its properties, and it will get soft, and eventually it will spoil. And the time itself is a factor. Okay. And second and more significantly for EV is cycle aging. The cycle aging is because of wear and tear that comes from actually using the battery. That means if we charge the battery up and discharge it by driving, then it will be coming under cycle aging. So every time you do this, we put a lot of mechanical and chemical stress on the battery's internal components. Because of that, cycle aging happened. Now, so what are the effects of this aging a driver would notice? The effect of aging comes in two primary ways, right? That is capacity fade and power fade. So capacity fade is most straightforward. It is like the consistent loss of battery's ability to store energy. So we can use the analogy of water bottle. So when the EV battery is new, it is like 1 liter bottle. It can hold a full 1 liter of energy. And after few years of use, due to irreversible chemical changes, the bottle will shrink here, right? And so this is representing the capacity fade, right? So bottle has shrink, let's say in volume, and it can only hold, let's say 0.8 liter of water. So this is representing the total loss of storage volume. So total loss of storage volume is capacity fade. So for an EV driver, This can be understood as the reduced driving range. The second is power fade, and this is caused by the battery's internal resistance. Let's go back to this water bottle. So imagine this, that the bottle's volume is shrinking, right? The volume is shrinking and its neck is also getting thinner or narrower. So now even if the bottle is full, you cannot discharge the water out as quickly as it was new. So narrowing of the neck of the water bottle is similar to what happens when the internal resistance of a battery increases. The battery struggles to deliver power rapidly. In an EV, this means that you will notice a sluggish acceleration, and it will also limit how fast you can charge the battery, especially at DC fast charger. So these two effects, capacity fade and power fade, happen simultaneously, and these define the aging process of the battery. Okay, so now we'll go one more step further and let's see what is actually happening at the microscopic level in an EV battery. So one of the most dominant and well-studied mechanism is SEI layer growth. The SEI, or the solid electrolyte interface, this is a microscopic film, and this forms on the surface of anode of the battery. That means the negative electrode of the battery. And it happens, the SEI formation, this happens during the very first charge of the battery. And this layer is actually very important. It acts like a selective filter, you can say. This SEI layer, this allows lithium ion to pass through here. You can see this is the SEI layer. This SEI layer allows lithium ion to pass, and it blocks the other component of the electrolyte. So without the SEI layer, the battery will fail. But this layer is not static. As the battery charges and discharges, the anode physically swells and shrinks. And because of this, there could be the tiniest cracks in the SEI layer. But there is an internal phenomena of the battery, that battery heals by itself by forming a new layer on top. And because of that, the total layer becomes more thick. It will be thicker over time. So this healing process of the battery has two negative consequences. First, it consumes the active lithium ions that can no longer be used for storing energy. And this is the direct cause of capacity fade. And the second is the thicker layer of SEI, it acts like a clogged filter. And this makes it harder for lithium ion to move through, right? So when the lithium ions are not moving freely in the battery, this will increase internal resistance, right? So another critical mechanism which happens especially in the stressful conditions is lithium plating. So normally during charging, the lithium ions are supposed to place themselves on the anode, and this process is called intercalation. So however, so when we try to charge quickly, right, especially in cold temperatures, the lithium ions cannot find their parking spot on the anode fast enough. So they just end up piling on the top of the surface of anode. And due to this, a layer of metallic lithium forms. And this is highly undesirable. This permanently removes these lithium ions from the energy storage cycle. And this causes a rapid, irreversible drop in capacity. And the worst part is that these metallic deposits can grow into sharp needle-like structures called dendrites. And this can make tiny holes in the separator here, which is there in between anode and cathode, right? And this can cause internal short circuit, and it can lead to fire also. This is one of the key reasons why a repeated and aggressive fast charging is not recommended for long life of a battery. Okay, right. Okay, so the good news in all of this is that the rate of degradation of an EV battery is not predetermined. It depends on how the battery is treated during its first life. So understanding these factors is very important. for, let's say, for the EV owners who want to maximize their battery's life, or for anyone who is trying to predict the future value of a used battery, right? So the first and foremost, we have high temperatures. So high temperature is number one enemy of lithium ion battery. The high temperature acts like a catalyst for all the unwanted chemical reactions we just discussed. The high temperature accelerates the aging process, right? And this is a critical consideration also in our country's climate, where in our country the ambient temperature can be very high in the most of the times. So therefore, an EV with good, effective liquid cooling system for battery will be much better in long run than the simple air cooled system. So the liquid cooling system, like we know that it uses coolant to directly remove heat from the battery cells, and air cooled system, it uses air to manage the battery temperature. Factor is aggressive fast charging. So the DC fast charging is could be convenient for long trips, right? But if we use the DC fast charging as a primary method of charging, it puts high stress on the battery, right? So pushing energy too quickly in the battery, it will generate more heat, and it increases the risk of side reactions like lithium plating. So therefore, the slower overnight AC charging is much gentle on the battery, and it is recommended for daily use, right? And the third is maintaining extreme state of charge, right? So a lithium ion battery will be most stressed and chemically unstable when they are either completely charged at full 100%, or it is completely empty at 0%. Okay, so fully charged at 100% and completely empty at 0%, both are very bad for the battery health, right? It's like if you leave your vehicle parked for weeks about 100% charge in the summer heat, this is one of the fastest way of degrading the battery life, right? So that is why most of the electric vehicle have some settings to limit the daily charge between 80 to 90%. And this is also recommended. This is between, if you charge the battery between 20 to 80%, this is a good consideration for battery health. Okay. And the last is the high depth of discharge. And this means how much battery capacity you use in a single cycle. Okay, so suppose there are two cases. Suppose we drive for 100% to 0%. So that is a deep discharge. And this is more stressful, very stressful. And it is more stressful than doing two smaller cycles, let's say for 80 to 30%. So 80 to 30% we are doing two times will be less stressful than doing 100% to 0%. That is a deep discharge, right? So why this is important for our topic today? Because these factors, that means if we have two identical batteries in two identical cars, that can have completely different health after 5 years, right? So suppose we have one electric vehicle or one battery which is used gently in cool climate, that can have suppose 95% of SOH or capacity left. And the second one is it is used aggressively in hot climate and always fast charge. So that the battery capacity may be down to 70% or 80%, right? And this leads to the important conclusion. The operational history of a battery during first life is the single most important data set for determining its true value and its true potential in its second life, right? Okay. So this brings us to finally understand the battery's first life. So when do we say a battery is finished? In the context of electric vehicle, end of life is a highly misleading term. It does not mean that the battery is dead or it has zero capacity, right? And it does not mean that the battery cannot provide peak performance, which is required for the vehicle, right? So the end of life of the battery means, it simply means that it is not useful for the electric vehicle, but it may be useful for another second life application. So for this, we have the industry specific term that is called state of health. SOH. So SOH tells us that how much our battery has aged, how much it has degraded. This is a simple percentage that compares the battery's current maximum capacity to its original capacity when it was new. So a brand new battery has an SOH of 100%. So after 5 years, if the capacity is faded by, let's say, 10%, so the SOH will be 90%. Right? So the generally accepted limit for retiring a battery from an EV is like 70 to 80%. When the SOH drops 70 to 80%. And why this specific number? So this number has come from the experience of several users, right? Okay, so we'll take an example here that if a car has a driving range of 400 kilometer when it was new with 100% SOH, right? So an SOH of 80% means the range is now 320 kilometers, right? So the SOH has dropped 20%. So battery, the range, kilometer range has dropped from 400% to 320 kilometers. In the similar way, the 70% SOH means the range is down to 280 kilometers. Okay. So at some point, the reduction in SOH will be inconvenient and it will trigger the range anxiety for the owners, right? So along with this, there will be an increase in internal resistance. That means the performance of EV will also suffer. The acceleration might feel sluggish, and the 30-minute fast charging that may take now 45 minutes or more, right? So with the drop of SOH, state of health, the battery will be also become less reliable and less predictable, and especially in extreme weather conditions, maybe too hot or too cold. So here the critical point of our entire discussion is that, so a retired battery with 80% SOH is not useless. It is a robust, highly engineered product that still holds 80% of its original energy. It is a valuable asset and this cannot be just thrown away. We can say that it is not suitable for high power variable demands of moving car, but a battery with 80% SOH is perfectly capable for serving in less demanding applications, less demanding stationary applications for many years, right? So the 80% of SOH, this is not the end point. We can say that this is a transition point. This is a gateway for batteries' first life to its second life. Right. So now we have seen the battery's initial life, starting from different aspects till its point of retirement from the vehicle around 80% of SOH. Now we enter to the next part of our discussion. What happens next? How do we transform this used component, right, the second life battery, into a valuable asset? So in this section, we'll walk through to the process of repurposing, right? And we will understand that how a retired EV battery pack is converted to a stationary energy storage system. We'll also take a look at the most critical and most challenging step in this entire process, that is the accurately and quickly assessing the health of each battery. And this will determine its value and the use and the place where it can be used. Okay. Right. So the journey from a used EV battery to a new storage product is not simple. This is a very sophisticated industrial process. It is not as simple like we are just talking that taking it out of the car and plugging it somewhere else. It is not that simple. So let's break it down into 5 stages. So the step 1 is collection and logistics. This is one of the major challenge in circular economy. So if we have to build repurposing, we will have to establish a vast network for safely collecting the retired battery packs from the thousands of car dealership, service centers, and the vehicle dismantlers across the country, and then transporting these heavy, potentially hazardous material to the central processing unit where we are going to do the repurposing. So this is a major operational hurdle, the collection and logistics. The second one is disassembly. And this is often the biggest hurdle in the entire process. So an EV battery, as we know, that it is a very complex high voltage system, and it weighs around hundreds of kilograms. So an EV battery pack needs to be carefully and safely dismantled by trained technicians. Anybody cannot do the dismantling of an EV battery, right? Because every car manufacturer designs their battery packs differently with different shapes, different connectors, different cooling systems. And above that, this process is almost entirely manual. It is slow, it is costly, and it is one of the main area where the industry needs more standardization in India, right? And the third is testing and grading. And this is the absolute core part. It's absolute the heart of whole operation. So once a battery is disassembled, each individual module will be connected to a specialized testing machine. The machine runs it through controlled charge and discharge cycles, and it precisely measures that what is the true remaining capacity, that means SOH, and the internal resistance of that particular battery pack, right? So testing and grading of a battery pack is like a diamond factory worker who is assessing a rough stone, right? And this is where the true value of the potential of the battery module will be determined. So this testing and grading is very important, right? And step 4 is regrouping and reassembly. Okay, so we cannot simply mix the old and new modules, or the healthy and weak modules cannot be mixed up in a single pack. This mixing will be very inefficient and unsafe because the weakest module would limit the performance of entire system. So based on the result of the test, the modules will be sorted with other modules of similar health, and these similar modules or the matched modules will be then reassembled into new pack configuration. After reassembling, and the important point is that here a brand new BMS, battery management system, will be installed. And this new BMS is the brain of the battery. So earlier it was programmed for EV. Now the BMS is programmed for different goals. So instead of high power for acceleration, the optimized BMS will provide a long, slow, and steady life in stationary applications, right? So step 5 is integration. So now the reassembled battery pack is now ready, and it will be integrated to a complete system, right? So an inverter will be added to convert it DC power to AC, along with some control softwares and some safety systems like fire suppression. And then after integrating all these, the the assembled battery pack along it will be used in buildings as a or any other place for like a battery energy storage system. Okay. So now we come to the most important part, the step 3, which we discussed, the testing and grading is very important because this is the absolute key for entire second life business model. Why? Because the price of second life battery is directly proportional to state of health. Okay, so and a battery module with 85% SOH is far more valuable than one with 70% SOH or 75% SOH, because the one with more SOH will store more energy and it will last longer in its second life, right? So a reliable, without a reliable, trustworthy, and fast SOH measurement, this whole process will be very much difficult, right? So the SOH estimation methods, these are important and for the whole circular economy. And these methods can be classified into direct method or indirect assessment method. So the direct assessment methods are the approaches in which the SOH is estimated directly from the remaining capacity of the batteries that is measured during testing phase, right? And the important point is that direct methods are non-destructive in nature. The battery will not be dismantled for direct assessment. The second is indirect assessment. So indirect assessment has three kinds of methods. The physical and chemical based method, then we have electrical based methods, and then we have AI based methods. So under the physical and chemical based methods, we have five different methods, and these methods depend on the nature of input source given to the battery for state of health estimation. So first there is a spectroscopy method, and this involves image processing of the battery's internal structure, and it analyzes the pores, gaps, or the size of atoms or any bulging of any chemical substance inside the battery. So the important thing is that in this method, the battery will have to be dismantled for getting the key insights of battery degradation. And these type of methods are not recommended for second life battery applications because the battery will be dismantled. Okay. Other than the spectroscopic method, we have acoustic method. And in this method, we pass acoustic waveform on the battery surface and we gather the reflected and transmitted waveform. Then the phase shift is compared, which occurs in during transmission and receiving end, right? And this is used for SOH estimation. Then we have this force method, and this in this force method, we measure the expansion or the contraction of forces inside the battery through some force measuring gauges, right? So in this method, the SOH is estimated from the magnitude of forces, which is measured by force gauges, right? Then we have thermal approach, or we can call it differential thermal voltammetry methods. So in these methods, we measure the temperature rise of the battery during charging and discharging phase. And then through the gradient of temperature voltage ratio, we estimate the SOH. Okay. Then we have the internal resistance method. And in this method, the heat generation of the cell using which is done using some joule calorie meter setup. And then this method checks the internal resistance variations with previous data, right? So the acoustic approach, the force, and this thermal approach, all other than spectroscopic, all these are non-destructive methods for SOH estimation. Then we have electrical based SOH estimation, right? So the change in magnitude of the electrical parameters such as internal resistance, open circuit voltage, impedance will be used to identify the battery degradation in these electrical based methods, right? So by comparing the present battery state to the new battery or the new nominal battery behavior, the SOH is directly measured, estimated in these methods, right? So there is impedance spectroscopy method, and in this method, we send small electrical pulses to the battery, and then we measure the response to estimate the state of health of the battery. So other than this, We have this ICDV, incremental capacity differential voltage method. Then we have DVIC, differential voltage incremental capacity method. Then we have charging curve method, then probability density function. So all these methods come under feature-based AI methods. And these methods require training and analysis of battery data sets to estimate the SOH, right? So these methods require some amount of previous battery history to find or to predict the SOH of the second life battery. Okay. But there is a problem with direct assessment. The direct assessment method, these are very slow. A full cycle can take up to maybe 4 or maybe 5 or maybe even more hours. So if we have thousands of module to test, right? So we can visualize that how this will create a massive processing bottleneck, and this will limit the cost of repurposing, and this will limit the scale also, right? So now the next is where the real innovation is happening. The industry is rapidly moving towards indirect method and more importantly, model-based methods. So these are the techniques which uses the data science or machine learning to estimate the SOH without doing full slow cycle. So under the AI methods, we have several kinds of methods like feed forward neural network, recurrent neural network, RBFN, then CNN, SVM, and so on. So these methods come under model-based AI methods. So in these methods, the feature or the parameter of interest is derived from feature-based AI methods, right? So for example, an algorithm of like these AI method, it can look at the shape of voltage curve during the first 10 minutes of the charging. So during the battery aging, the voltage curve will not change much. There will be only subtle or predictable changes. So by comparing the curve of the used battery to a library of data sets from thousands of other batteries, the algorithm can make a highly accurate guess of SOH, right? So the main point here is that to reduce the testing time from hours to minute. And this is the key area for R&D for startups in India and around the world, right? So to reduce the testing time from hours to minute. So there is one startup in India, Repurpose Energy, right? And they are developing technology to do SOH estimation in only 15 to 20 minutes. So the core point is, so the crux of the talk is that whosoever cracks the code for fast, cheap, and accurate estimate SOH estimation, that will hold the major key for unlocking the profit of second life industry. Okay, so we have discussed that how we can repurpose our battery back into new certified energy storage system. The next question is, where do we deploy it? Okay, so in this section, we will explore the most promising applications where these batteries can be deployed, the applications which are specifically made for India's unique energy needs, right? And then we will summarize the value proposition which the second life battery systems offer across different dimensions, such as economic, environmental, or strategic. And finally, we'll provide a balanced, realistic picture, and we will see the real hurdles which are coming and which industry is facing for the wider adoption of second life batteries. Right. So now we can see that the applications of second life battery, as we have talked earlier also, that these applications perfectly align with India's energy challenges, right? So as the second life batteries are stationary, their low energy density compared to the new battery does not matter. The only thing which matter is low cost and reliability. Okay, so one of the biggest and most significant application of second life batteries in India is renewable energy integration. So India has a massive national target for solar and wind power. But the problem is that we know that wind and solar, these sources are intermittent in nature. So here comes the second life batteries. Second life battery systems can act like a giant power bank, which can store excess solar energy during the sunny afternoon. And this energy can be released during the peak demand hours in the evening. So this integration with integration of second life batteries with renewable energy, this will smooth out the fluctuation. It will make the grid more stable and it will allow us to integrate more renewables without compromising reliability, right? The second is the second huge market for second life batteries is backup power, right? So we are all familiar with the sounds of diesel generators, which kicks in during the power cut. So second life batteries are an alternative for this. It can be alternative for the thousands of telecom towers across the country, for commercial buildings, for hospitals, and even for residential complexes. The second life batteries can provide backup power, and that backup power will be silent, emission free, and there will be instant backup power. So second life batteries is a direct replacement of diesel generators, and this reduces the pollution, noise, and maintenance heavy technology. Right. So the third is the second life batteries can also provide valuable grid support services. Right. So a large second life battery installations can be used for peak shaving. That means discharging power during the few hours of the day when electricity demand is highest. And as we know, the peak shaving is an energy management strategy which is used by large electricity consumers. And the primary goal of peak shaving is to reduce or eliminate the costly demand charges that comes because of the single highest spike. So utilizing second life battery for peak shaving, this will reduce the strain on entire grid and it will be beneficial for the system, right? So that there is one project in Delhi, the Tata Power's battery storage project in Delhi. This is a pilot project for exactly this kind of service. And the second life batteries can be seen as future low cost way to scale these solutions, right? Fourth is EV charging infrastructure support. Okay, so to build a wide network of DC fast charger, we will have to make expensive upgrade to the local electricity grid. But there is a smarter way with second life batteries. We can co-establish a second life battery system at the charging station. And the second life battery can charge slowly from the grid during off-peak hours, and then it can discharge into the car when it plugs in. The second life batteries can act as a buffer. We have a real world example also for this right here in India. You can see here in this diagram. This is the collaboration between MG Motors and the startup Batex Energy. They have created an off-grid solar powered EV charging station using repurposed MG batteries, right? So finally, uh, there is also very high potential in rural electrification. We can pair the low cost solar panels with low cost second life batteries, and it can create the robust microgrids. And this can bring reliable power to the communities and to the small businesses which are currently off grid and which are currently suffering from poor grid quality. Right. So now we can summarize the value proposition. The benefits of developing second life battery ecosystems are clear, but there are some challenges also. So we'll see first the benefits. So economically, the main benefit is lower capital cost. Okay. So the second life batteries are about 30 to 70% cheaper than a new battery for the same capacity. Second life batteries can make, the another point is that the second life batteries can make energy storage projects very attractive, right? Which was not the case earlier. So such utilization of second life batteries, this will literally create the value from these the waste which was we can use the batteries as an asset, which was previously considered as waste. If we just throw it away, or it if we are sending it only for recycling, right? So second is environmental. So environmentally also, this is a huge win for circular economy. We are extending the useful life of a resource intensive product, right? We are delaying the need for recycling. And most importantly, we will avoid the carbon, we will reduce the carbon footprint, which can come due to the manufacturing of brand new batteries, right? Third, strategy wise also, this helps the second life batteries helps in building domestic green tech industry. It will create skilled jobs. It will provide storage infrastructure, and this is required for supporting India's renewable energy ambitions. And this is also required to strengthen our grid. However, we'll have to be realistic, and we will also have to acknowledge the significant challenges that a second life battery industry can face. So the first is technically the lack of standardization in battery pack design, and this is the most critical issue for the repurposing company. Every pack is different for disassembling and getting access to the reliable data from the first life, from its first life, right? Like temperature history or charging patterns. So all these are very difficult, and this creates challenges in predicting the remaining useful life or the future performance of second life batteries. So these are the technical challenges. Then we have economical challenges also. There is a constant race against time because the price of brand new LFP batteries, particularly from China, this the price is falling rapidly. And the business of second life batteries depend on maintaining the significant price advantage, right? So if all in cost of repurposing used battery gets close to the price of new one, the market will collapse. And this puts too much pressure on the repurposing company, and they will have to innovate to drive down the processing cost. So this is the economic challenge. And finally, we have logistical and regulatory challenges also. So to set up a nationwide network for collecting millions of used battery, this is a massive task. And as of today, we lack specific Indian standards from the BIS and for the safety and performance of second life battery systems. And because of this, the customers and the investors are hesitant, and this creates uncertainty in the market. So overcoming these challenges is a central task for the policymakers and for the industry, right? So now we'll move our discussion to the Indian ecosystems and the players which are playing a big role in second life batteries. So in this final major section of our lecture, we will focus on Indian ecosystem, right? So for all this, an industry, the second life battery industry, this requires a carefully constructed framework of policies. It requires the vibrant community of innovators, and it also requires clear vision for future, right? So we will start this by examining key government policies which are shaping the second life battery industry. We will see the high level strategic plan, which is set up by Niti Aayog and some other groundbreaking regulations also, which are making the circular economy. And then we will see some of the Indian companies on ground who are doing the actual work of building this industry. And then finally, we'll see the what is the road ahead for India and how we can proceed further. So that we will see. Right. So there are many policies that support EV ecosystem in India. So if there is one single piece of law or regulations that you should know, it is battery waste management rules of 2022. If you are working in this area. So this is a game changer for entire end of life battery industry in India. So the BWM rules, these are built on a powerful principle, that is EPR, extended producer responsibility. In simple terms, this means the company that produces or imports a battery, the vehicle OEM company, is legally and financially responsible for ensuring the battery is managed properly till its end of life. The company's responsibility does not end when the car is sold. It remained throughout for the entire life cycle of the product, right? So EPR is a central mechanism. The rules are comprehensive and strict, and EPR also make it illegal to simply dump or batteries in landfills or burn them. We cannot burn the batteries, right? So the producers or the manufacturers are required to set up the collection networks to ensure that the batteries they are collecting are sent for recycling or for refurbishment, right? And to ensure this, to ensure the transparency and to prevent fraud, this entire system is managed through a central online portal, that is Central Pollution Control Board, CPCB. And this applies to all kind of batteries. So there is a provision also for of penalty for producers if they fail to meet the defined EPR targets or obligations. So this diagram right hand side, this illustrates the EPR framework, which is the central pillar of India's BWM rules. And this maps the entire life cycle of a battery, and it also shows the responsibilities which comes under circular economy. So first we have the producers, the manufacturers. So this is where the cycle begins, right? The producers introduce new batteries into the market. Then we have here the consumers and bulk users, and these uses the battery until the battery reaches their end of first life. So the waste batteries or the first end of the batteries after end of first life will be segregated and returned through the system which is established by the producers, right? So at the end of first life, this BWM rule, this imposes a critical consideration. The end of first life batteries, this cannot go to the landfill, and these batteries should be directed to authorized processors. Then comes the collection and processing. The end of After the end of first life, these batteries will be sent for two main things. The first is refurbishers, right? Okay. So the used batteries, which are good enough, will be sent for refurbishing, right? So in the refurbishing, they can have repairing, reconditioning, or repurposing so that the batteries can have a second life before they finally retire. So the batteries that cannot be refurbished, those will be sent for recycling. That is the final processing. So after this, if the batteries are sent for recycling, the recovered materials will be the end product of recycling. So these materials must be incorporated. This is a law of BWM. So these materials, the recovered materials, must be incorporated back to the for the manufacturing of new batteries. And this completes the entire circular loop. And this also reduces the dependency on imported materials, imported cobalt, etc. So as I told you earlier, that the entire system is monitored and managed through CPCB. That is an online mechanism, and CPCB maintains it through a digital platform, right? And all producers, recyclers, refurbishers have to register on this portal, and they have to file regular returns about their sales, collection, and processing volumes. Then there is EPR certificates also, and this is the core compliance tool. The recyclers, refurbisher generates EPR certificates based on the quantity of waste battery which they have processed. So what we have seen, the rules are clear, and these rules have time-bound targets, right? So there is one more point here that, for example, the producers of EV batteries, they have to ensure that they collect 70% of the battery which they have put into the market by 2027-28. And for the batteries that are recycled, there is a target that they have to recover 90% of the material by weight. And there is a mandate in rules also that the recovered material should be sent back to the manufacturing of new batteries, as I told you earlier. So the new batteries must contain a minimum percentage of recycled materials. And this creates a guaranteed market for the recycling industry or for the circular economy. So the BWM rules, these are the foundations upon which the India's circular economy will be built. Right. So beyond the BWM rules, we have several other policies also which supports in ecosystem of second life batteries in India. So at the highest level, we have this the vision led by the Niti Aayog, which is the government's think tank. They analyze the challenges and they recommend a path forward. And this shows that the government is also thinking sincerely about this ecosystem. Then we have different EV adoption schemes, like this FAME 2 scheme was very helpful in making EVs affordable, and this was responsible for driving the initial wave of EV adoption in India. Under FAME 2, the majority of EV were purchased, and these purchased EVs were two-wheelers and three-wheelers, which are dominating the road. Now the FAME 2 has been ended, but we have PME Drive scheme, which is now providing support. And this is helping in the growth of electric vehicles. And also, if it is helping electric vehicles growth, it is also helping the future of retired EV batteries. Okay, so another very important development is Niti Aayog's this draft battery swapping policy. And these policies focus on creating standards, right? So that the batteries can be interoperable. That means a battery from one company can be used in another company's vehicle or swapping station. And if due to this, more standardized battery pack are designed, it will be a massive advantage for second life industry. And this will create disassembly and testing process much easier and simpler. Then we have a crucial role of BIS, Bureau of Indian Standards. Currently, we have some standards like IS 16046. This exists for the safety and performance of second life batteries, right? But there is some gap also. We have some regulatory gap also. We do not have a specific BIS standard for second life battery systems. And this is absolutely necessary to develop these standards. These standards are absolutely necessary. And because this will be if we are able to develop the BIS standards for second life battery systems, this will be an important step for ensuring the safety and reliability of second life batteries. And this is also is very important for building trust with customers and other entities, right? Okay, so we can say that in overall, policy creates environment, but it's the researcher or the startups who build the industry. So in this section, we'll move towards the actual place where the work is being conducted. So we will look at some of the dynamic Indian startups, right? So here, right. So India is very fortunate to have these growing startup ecosystem, which are and these startups are tackling the second life battery challenges, right? So let's see some of the few key players in India who are doing this, right? So first we have here the Loham Clean Tech, and this is a great example of an integrated player. So Loham Clean Tech, they are doing majority of work. They manufacture new batteries. They repurpose used batteries into second life energy storage systems for homes or for businesses. And they have an advanced facility also to recycle batteries which are useless, right? So what we have seen that Loham Cleantech, they are manufacturing, they are repurposing, and they are also recycling. And they have also announced a partnership with MG Motors India for developing some second life solutions for EV batteries also. Right. So then we have another important startup, that is Batex Energies, and their primary focus is on back-end recycling. So Batex Energy, they use advanced methods like hydrometallurgical process for extracting the lithium, cobalt, or nickel from the battery, the retired batteries, or from the battery scrap. And they are and these Batex Energy, they mostly, which I have seen, they are sending the recycled materials to different industries. And the Batex Energy, they are also active in Second Life, as we have discussed in one of the slide, that their collaboration with MG Motors India, they have created the India's first off-grid solar powered EV charging stations using repurposed batteries. And this is a landmark project of India, right? So then we have here the startups like New Nam. This is based in Bangalore, and this startup focuses on using second life batteries, the batteries from like old laptops or electric vehicles, and they try to provide energy access to the underprivileged community. The new name, this startup, they create small portable power packs, and that this and they provide these power packs to the street vendors so that they can light up their cars at night, and they provide it in village shops so that they can run a fan or charge phones. And this type of activities, these activities demonstrate a powerful grassroots application of second life batteries, right? So then we have okay, by mistake it was clicked. Okay, so now we have the another innovative uh, companies, this Tracks Clean Tech. And this Tracks Clean Tech, they are focusing majorly on the AI-based technology so that they can extend the battery life. Then we have Vision Mechatronics, and they are working on for developing advanced diagnostic tools for modular packs, right? So in all together, these companies, these are the few companies we are working in this area, and we have many more. And these companies are building the technological and business model foundations for India's circular economy in batteries, right? So now, we have explored many things. We have explored the context, the technology, the applications, and the key players. So in our final section, we'll zoom back to the big picture. We will see how second life batteries are not an end. This is a critical link to the much larger goal, that is the circular economy. And finally, we will conclude the summary and what is the road ahead for India and what could be some of the key recommendations for all stakeholders. Right. So this brings us to the final vision, that is full circular economy for EV batteries. So for decades, the industrial model has been linear. We take the resources from Earth, we make a product, and at the end of life, we dispose it as a waste. So this was the linear industrial model, which used to be. The circular economy, the aim of circular economy is to break this and to convert this into a loop, right? So second life battery are the foundation of this vision for EV industry. So let's see the ideal journey of a battery in this model. So it starts with first life, right? It starts its first life in demanding application like car, okay, where it serves around 8 to 10 years until its capacity fades to around 80%. Its SOH left to 80%, right? So in circular economy, instead of discarding the batteries, it enters to the second life. Here, then the batteries are repurposed into less demanding second life stationary energy storage system. In this role, the battery continue to operate effectively for another 7 to 8 years, maybe for 10 years, until the state of health drops to a level, say, let's say 30 to 40%, right? And this will be the time when the battery will no longer be useful even for backup power. So after the battery has been, the utility of the battery has been maximized into two separate life cycles, first life and second life. Only then it reaches to its true end of life. At this point, it is sent to the recycling facility. So here, the advanced methods are used, like hydrometallurgy are used to break down the battery and recover the valuable raw materials inside, like lithium, cobalt, nickel, etc., with a recovery rate of more than 90%. And these recovered materials will then be sent right back to the manufacturers, the cell manufacturers, for creating the brand new batteries, right? So what we have seen, the first life, then second life, then recycling, and then the recycled materials are being sent for manufacturing the new batteries, and then the new batteries are then again being used for first life applications like in EV cars. So this closes the loop, and this is called actual circular economy. So this model of the earlier model of cascading use and this model of the closed loop from high power application to lower power and then material recovery, this is the core of true circular economy. And this ensures that we extract the absolute maximum economic and environmental value from the EV battery. Here comes one of the very important parameter which should be there in Indian ecosystem. So this diagram shows the battery passport, right? And this shows the journey of a battery from its creation to its end of life. Okay, and this tells us about the battery passport, and this battery passport is actually a digital record for every stage of a battery. And this passport, the main purpose of designing this passport is to increase transparency, to promote sustainability, and to enable circular economy. So at the very first, we have sourcing and manufacturing, right? So this is the very beginning of the battery's life. This involves the mining and processing raw materials like lithium, cobalt, and then manufacturing them into battery cells and packs. So at the initial stage, when the battery is being manufactured, the passport will be created, the battery passport. And this battery passport records the crucial information about the battery's origin, including the geographical source of raw materials, which, which were used to manufacture this battery. And this ensures that the battery materials are ethically and sustainably sourced, right? This battery passport, this also contain carbon footprint data. That means the data for energy consumed and emissions produced during manufacturing, right? Okay. And this battery passport also contains manufacturer details and production rate also. Then the battery passport contains data about the first life in electric vehicle, where the batteries goes thousands of charging and discharging cycles. So throughout its life in electric vehicle, the passport is continuously updated with dynamic data, right? And the battery passport, we can say that it is a living document. So the battery passport in when it is used in EV, it contains the performance data such as the charging history, operating temperature and energy, the state of health, repair history, and so on, right? So then comes the end of life, first life. So, so after the end of first life, the battery passport will be very useful for all stakeholders. So the battery passport, it will allow the repurposing company to make the correct decision about the battery's future. So based on the SOH and overall condition of the battery, it is determined, it is decided that whether the battery is suitable for less demanding application or it should be sent for recycling, right? So then comes the second life, the repurposing for BESS. So if the battery is still healthy enough, it is repurposed for stationary application such as BESS. So now the mode of battery passport will change. The journey of battery passport will change, right? So earlier it was being used, the first it was used to for the initial history of the battery. Then it includes the history of its first life, and now it it starts its journey in BESS, where it tracks the performance, the degradation of the battery in along with BESS until the battery reaches its true end of life. Then comes the final end of life and recycling. So after its second life, the battery capacity fades, we know that, and it will fade to a point that it will not be economically useful for any application. So this is the true end of life of a battery. So a battery passport plays a very important role here. It provides the precise information to the recyclers about the battery's composition and internal structure. And this is very important for safe disassembly and efficient recovery of the materials which are inside the battery. So we can see that the implementation of battery passport is absolutely necessary for circular economy, and it should be implemented straight away in India, in Indian ecosystem. But what we have observed that we have several gaps in our EV battery regulatory framework. So then the first is the regulatory gaps for second life applications. So what we have seen that there is no dedicated second life framework. The BWMR, the Battery Waste Management Rule 2022, it focuses on recycling. The BWM rule, this neglects the safety and certification standards for the repurposed battery, right? And India also lacks testing and certification standards and protocols for SOH and remaining useful life assessment, right? Then there is some undefined categories also. The regulations do not differentiate between reuse, repurpose, refurbishment, and recycling. This is one of the important points which should be taken care of. Then we also lack digital traceability and battery passport, which we have discussed just now in the previous slide. So in unlike European Union, they have a separate mandate, and then China they are having a unique ID regime. The India's battery passport is this initiative. It is still in planning stage. It is not implemented yet, right? And then there is an absence of digital repository also about the battery origin, its composition, and because of this, it hampers the enforcement of EPR and quality assurance also, right? Then third is there is informal sector dominance. Nearly 90% of the battery waste is processed informally using unsafe methods. There are lots of recyclers in Uttar Pradesh also, in many in several states of the country, and these informal recyclers are excluded from EPR, right? So the policy should be there that the recyclers should be trained, and the policy must certify these companies to formalize the required practices, right? So now the fourth, there is also an institutional fragmentation and policy coordination issue. The responsibilities of battery circularity, the circular economy, it is divided. It is spread across several ministries, such as Ministry of Environment, Forest and Climate Change. Some of the things this ministry is handling. Then Ministry of Heavy Industries, Ministry of Mines, right? So several ministries are included in the policy making. So this is delaying the decision making. So there should be a single nodal agency, or there should be a task force which can coordinate with all these ministries. This is essential for the implementation and strategy formulation. Then fifth, we have inadequate EPR pricing. In India, the EPR floor price is only 120 per kg for EV batteries for the recycling, recycling the materials. And this is less than one-fourth of the UK benchmark, where it is 586 rupees per kg. And due to there is a loss in covering recycling cost, and this motivates fraud practices. So what is recommended? It is recommended that in India also the EPR price should be at least 400 to 500 per kg, and this will ensure a proper material recovery, and this will also discourage the hazardous dumping of batteries. Then we already have seen that we have weak implementation and enforcement, right? And we have weak infrastructure and reverse logistics also. We do not have proper collection networks. Over one-third of retired batteries, these don't go to the formal channels due to scarcity of collection centers, especially in rural areas. We have not implemented standardized protocols for temperature control, or for fire suppression, or for training or handling the different people who are involved. And these leads to the hazardous conditions that can appear anytime, right? So what is the road ahead for India? So we have seen that the opportunity, the second life battery industry, this is huge, but there are challenges also. So building second life industry, this requires a coordinated push from all the stakeholders, whether this is government, whether this is a repurposing company, whether these are the users, the refurbisher, recyclers, all, right? So the immediate proper priorities are clear, which we have discussed for the policymakers and government. And there is a need to develop and notify specific BIS standards for second life battery systems. So if it is done, it will provide a quality and safety assurance for second life battery market, which India needs. We also need to ensure the strong enforcement of the battery waste management rules, right? There has been a draft of BWM rules of 23, but most of the things are not implemented yet. And most of the things are in planning stage. So there should be additional clauses to prioritize repurposing before a battery is sent for recycling. Okay. And for the industries and startups, there should be, the main thing is collaboration. The vehicle manufacturers, they need to work more closely with repurposing company. This means they should share the critical battery health data to the startups, to the researchers, and the main idea of battery passport, this should be incorporated, right? And they should think, the startups, the industry, they should think about better design, which can avoid disassembly of the batteries, because this will improve, this will push the second life industry, and this will make the repurposing process much easier, right? And the focus on R&D is also required to bring down the cost of testing and the time also, right? We'll have to develop the advanced algorithm so that we can bring down the time to few minutes, right? And for our colleagues in academia or research, we need better, more accurate models that can predict how batteries ages, how a battery, how an EV battery degrades. And we need continued motivation, continued innovation and recycling technology also, right? And this will ensure the final step for the circular economy. And this should be efficient and environmental friendly. So in conclusion, the second life batteries in India is just beginning, which is to be written by the Indian startups, by the government of India, and by the academia. And but there is one more point here, that there is a fundamental tension that needs to be managed. And what is that? The startups are pushing the innovation in second life, but the larger established companies, they are focusing on recycling because they deal with economics, which is very predictable. And this is playing a major role. So there is a need to bridge this gap so that we can ensure the batteries, the batteries after the end of first life, the valuable batteries are repurposed instead of recycling. So this path is the second life battery industry. This is complex, but this is worth it. And it will be clearly very beneficial for our future. So by turning today's waste, we can make it the tomorrow's asset. And India can strengthen its energy security. We can achieve our climate goals of net zero emissions by 2070. And we can position, India can position itself as a true global leader in the sustainable technology of 21st century, right? So with this, I'll conclude here. I hope the points which I have kept here, or I was able to give you some insights about the second life batteries, its some information, and what should be the path forward, right? So thank you very much for listening me, right? So I know I can see that around 15 or so participants are joined here. Okay, thank you very much. I received a message here, something. So if you have any questions, you can write into the chat box. I'll try to answer, or maybe today, because tomorrow is Diwali and maybe many of you will be busy at your homes, right? So what you can do, if you have any questions, you can directly mail me, or on my mail, that is dweepak underscore kumar at the rate mnnit.ac.in, right? So if you have any doubt, any queries, any questions, you can mail me on that, and I'll try to answer your queries. Or if and in MNIT also, we will currently there is no lab for this lab or testing facility, but with the coordination of the Institute of Authorities, we will try to develop some labs. So when it is developed, so any of you would like to collaborate with us, that can also be done. Right. So if there are no questions, I can see that there no question has been given in the chat box. Right. Thank you very much, Devrat, and thank you very much, Dr. NDV Prasad. So what we can do, if there are no further questions, we can close this session. And you can anytime, you can send me your queries. I'll try to answer. And a very happy Diwali to all of you. Right. So if we can close this session now, as there are no questions. Thank you very much. So on behalf of the organizing committee, so I think this was the last lecture of the FDP. So on behalf of the organizing committee and the organizing team, I thank all of you for joining us and for attending all the sessions. So no, there is one more lecture, I think, from 2 to 4. Yes. So after 2 to 4, that will be the last lecture. And at 4 p.m. we have the valedictory program for this FDP. So all of you are requested to join in FDP to share your views about the FDP. Right. Okay, so we'll close this session. Thank you very much for joining and listening me. Thank you very much.